Hello students, welcome back. Today we're going to be continuing with limit of a function. So last time we completed two examples, and now let's go ahead and talk about the limit loss. So the limit loss, suppose that c is a constant and the limit of f of x as x approaches a, and limit of g of x as x approaches a exist. Then we have the following five laws. Right, so we can distribute limits over addition, subtraction, we can distribute the limit over constant multiplication, and multiplication. We can also distribute the limit over the multiplication of functions, division of functions, as long as the limit as g of x as x approaches a is not equal to 0. Okay, so essentially the first one is the sum law, second one is the difference law, third one is constant multiple law, then product law, and quotient law. So okay, so all of those laws we can apply in order for us to solve problems, right? So perfect. Now we have a few more laws that we should discuss, right? Which are a little bit more important than the basic ones. So the sixth law is going to be the power law. So the power law is essentially the law of power. So if limit of f of x to the power of a, right? So specifically the function to the power of n, then it's going to be the same thing as first we're taking the limit of a function and then you raise it to the power. Okay. Then we also need to define a little further what does that mean to apply the limit. So we have to include a few more rules. So the seventh rule is that limit as x approaches a over c or x itself is going to be c and effectively. Okay, then we would also have the ninth law, where if we have limit as x approaches a of x to the power of n is equal to a to the power of n, where n is a positive integer. Okay, and then the last one is not the last one, actually, is the root law, right? So the power also we can apply it to the root, right? Because, well, if you remember from algebra, the root of a function is just a power, so it's a function to the power of 1 over n. Okay, and then the last one is pretty important. It's going to be the root law, right? So we call it a root law. Okay, so here, 11 most important rules, right? Majority of the time, we just use the first 6, right? The first 6, that's where the majority of them coming. So the last 4, the last 5 are less common. But for example, let's go ahead and take a look at our first example of today. So we will have that we want to find limit as x approaches 5 of 2x squared minus 3x plus 4. Right, so we're going to be referencing the first 5, right? 5 and the fifth law, and of course we'll reference the ninth law. So the first 5 laws and the ninth law. So let's go ahead and apply it. So the first thing is we can distribute it. We can distribute this. So it's going to be limit as x approaches 5 of 2x squared minus limit as x approaches 5 of 3x plus limit as x approaches 5 of 4. Okay, so by law 2(1), now we're going to be applying the law of 3. So we're going to have limit as x approaches 5, x squared minus 3 limit 5x, and then plus limit approaches 5, 4. Right? So now, right after applying the essentially, the third law, now we're going to be applying 9, 8, 7. Right? So we will have that 2 times 5 squared minus 3 times 5 plus 4, which will give us an answer of 59. Right? So the limit of that quadratic equation is 59. Okay, now let's go ahead and take a look at the second example. So example 2. Here, let's go ahead and take a fraction. So limit as x approaches -2 of x cubed plus 2x squared minus 1 over 5 minus 3x. Okay, so here we can apply the law of 5, right? The rule number 5. So we're going to have limit as x approaches -2, x cubed plus 2x squared minus 1 divided by limit of x approaches 2 of 5 minus 4. Okay, so now by using the first 3 laws, we're going to have limit as x approaches of x plus 2 times limit of x approaches 2 minus limit of x of 1. Okay, divided by limit as x to 5 minus 3 right times of x approaches negative. Okay, and now by using the law 789, we will have -2 cubed plus 2 times divided by 5 minus 3 times 2. So after, right? So now as you practice, you'll get better and better at computing. So you can skip a few steps and get faster to, right? So one of the important things you can notice is we can use direct substitution property, right? So some functions we're able to direct substitute. So direct substitution property, if f is a polynomial or a rational function and a is in the domain, right? So by being in domain of f, that means that that a is not essentially violating division by 0, right? Then we can just direct substitute, right? Later on, we're going to find out that it means that the function is continuous, right? This is going to be called continuous. Okay, so for example, how would we solve a limit like this? Go ahead and take the following example. So example 3. So we will have limit as x approaches 1 of x squared minus 1 over x. Right, if we plug in 1 right now, we're going to get that it's 0 over 0, so it's undefined. So let's go ahead and try to simplify. We're going to have limit as x of, so we can factor out the numerator. It's going to be x plus 1 times, okay, all over minus 1. So clearly, minus 1 cancel out. Limit of x plus 1 is a linear polynomial, right? It's a linear equation, so we can plug it in. Okay, pretty straightforward. Okay, so now, okay, we can also do, right? We can also do following. So remember, last we said what it means for the limit to. Now, essentially, that's going to be our theorem. So theorem 1. So limit of x approaches a of f of x equal to L if the left hand limit of f of x and the right hand limit are both equal value. In this case, L. Right, that's going to be our theorem. And we always have to check from the left. And usually graphical where we can let's take a look at one example here. So, example 4. So a very common function would be y equals absolute value of x, right? So if we graph that function, looking like a wedge. So now we know from the left side we have, so x is equal to x and negative x. So it's negative x if this is less than 0, and it's positive x if x is greater or equal. Okay, so if we take limit as x approaches 0 from the right, of absolute value of x. So from the right, what do we have on the right side? We have the x. It's going to be limit of x approaches 0, right? And that's going to be right because we're approaching it 0. How about limit as 0 from the left of x? Well, that's going to be limit of x approaches 0 negative factor. Well, it will also turn out to be 0. Good. Right, it's also going to be 0. So that means by the theorem, since both of them agree, right, both left-hand side and the right-hand side limit agree, then the limit 0, the value of x, is also going to be. Okay. Meanwhile, sometimes the limits are not going to agree. Let's take a look at next example. So example 5. So let's say we want to compute limit as x approaches 0 of absolute value of x over x. So if we graph that, we will have the following picture. So y is equal to the value of x. So we're going to have the following. Let's try to, clearly as x 0 from the right x, which is going to be a limit of x approaches 0 from the right. So from previous problem, it's going to be x over x. So that simply is going to be right, just going to be 1. Then from the left hand side, we're approaching 0 from the left of absolute value of x over x, which is equal to limit of x negative x, which is going to be equal to, same thing, negative. Right, so now from the right side, we're going to have a positive 1. From the left side, negative 1. They are not equal, right? Those two things not equal. So if they're not equal, that means it does not exist. This one does not. Okay, so essentially, we always want to check that both left-hand limit and the right-hand limit exist. Okay, now our second theorem. Second theorem is going to be the following. So, limit comparison. Theorem 2. If f of x and g of x is such that f of x is less than or equal to g when x is near a, possibly at a, and the limits of f and g both exist as x approaches a, then the limit of f of x is going to be less than or equal to the limit. Okay, and well, this property will help us because we can develop a very famous calculus theorem, right? And that calculus theorem is called the squeeze theorem, right? It has many names in calculus, right? It depends on the book and depends on the source that you're looking at. It might be called a squeeze theorem or standard theorem or pinching theorem. So, but essentially, it states the following. So, if f of x is less than or equal to g of x, and it's less than or equal to h of x when x is near a, except possibly at a, and the limit of f of x as x approaches a and limit of h of x a is equal to L, then it must be that limit of g of x as x approaches a must also be L. Okay, and so kind of a graphical representation of the statement would be the following. So if we take a closer look, so let's say the green function is our h, the red function is our g, and the blue function is f. So we can clearly see that the function h and f are squeezing or sandwiching the g. So that means they must be, so the g must have the same limit f did. Okay, so an example, right? An example for this theorem. So example 7 here. So we're gonna have that limit of x approaches 0 of x squared times sine. Okay, so now in this case we cannot separate them, right? We cannot use the rule because limit as x approaches 0 of sine of 1 over x does not exist, right? We do have to use squeeze theory. Okay, but what do we need to notice? So what is the range, right, of sine of 1 over x? So the range is, well, like as a regular sign, it's going to be from -1 to 1. Right? If we go ahead and multiply, right? If we go ahead and multiply both sides by x squared, we're going to have a negative x squared less than or equal to x squared sine of 1 over less than or equal to x squared. Okay, so from here, we know what the limit of x approaches 0 of x squared is. It would be 0. Same thing for limit as x approaches 0 of negative x squared. It's also going to be 0. Right, so that means by square's theorem, the limit of x approaches 0, x squared times sine, also going to be equal to 0. Okay, here we can take a look at the drawing of how it would look like. So essentially this function has the following, right? And this top function would be x squared, the bottom would be negative x. You have both of them bounding it, right? So when we're approaching 0, they actually, all of them will be approaching 0. All right, perfect. Now, let's go ahead and give a precise definition of a limit. We haven't yet done a precise definition. But now, let's go ahead and introduce our epsilon delta definition of official calculus. So, that definition is going to be as following. So, let f be a function defined in some open interval that contains the number a except possibly at a itself. Then we say that the limit of f of x as x approaches a is L, and we write it like this. If for every number epsilon greater than 0, there is a number delta greater than 0, such that if x is in the range of delta, then f of x minus L is less than epsilon. So the reason why we have it as epsilon, and the reason why we have it as an absolute value is because we are covering two definitions, right? We're covering definition for the limit from the left and limit from the right. So because on the both sides, right? On the both sides, we cannot do it from one side, right? We cannot do it from one side. We have to make sure that we approaching both from the left side and the right side. This definition incorporates, right? Incorporates the both, right? If we were traveling from the left, right? So because if we look at this, so 0 less than absolute value of x minus a less than delta, right? So what would that be? That would be negative delta less than x minus a less than, right? So this is from the left, this is from the right, right? If we're thinking about the right. Similarly, for f of x minus L being less, okay, what would that be? That would be L minus f of x less than f of x, L plus f. Right? Again, we're approaching, the right side is approaching the right. The left side is approaching the left, right? So here we are hiding, essentially, in the definition, hiding the left limit, side limit, right-hand side. Okay? So we want to be able to be as close as possible to the value, right? We are the ones who are defining that. So here would be an iteration of our definition, right? So we have a function, we try and approach it. So we want to find the limit in that interval. So the epsilon is going to be right here. We want to be as close as possible to the point, right? In both x and y, so we can perfectly define it, right? So epsilon, we are the ones in control of epsilon. So as we get the epsilon, right? So epsilon will dictate our delta, right? So once we choose an epsilon, we can find a delta, right? And the smaller the epsilon, the smaller the delta is. So, and we can essentially approach it to be exactly that point. Right? This is a point of the calculus. So, for example, right? If we wanted to do some proof, right? Let's say the following. Take a look. example. Example 2. So we're going to have proof that limit of x approaching 3 of 4x minus 5 is equal. We want to use the epsilon definition. So proof. So what will that be? We want to say that epsilon be greater than 0, right? We want to find delta such that 0 x minus 3 less than delta will give us what? Will give us that 4x minus 5 minus 7, right, is going to be less than. Okay, but let's go ahead and actually work out the absolute value of 4x minus 5 minus, right, that's going to be the same thing as 4x minus 12, which is equal to 4 times x minus 4, right? And what we can do, we factor out the 4, because positive, right? It's going to be 4 times x minus 3. Perfect. So that means we'll say that if, right, so we want to have 0 x minus 3 delta, then we're going to have 4x. So solving for this expression is going to be x minus 3 got to be less than epsilon over 4. So whatever epsilon we choose, we have to divide it by 4 in order for us to get it. Okay, so that means what do you guys think? What should we choose? Delta? Delta should be equal to this. So delta going to be epsilon over 4. Okay, so because we have to be less than epsilon, right, all the time. So okay, so that means this is going to be less than epsilon. So that means 4x minus 5 minus 7. Vacation, we're going to get 4x minus 3. And since x minus 3 is less than epsilon 4, so that's going to be less than 4 delta. And 4 delta is over 4, so it's going to have 4 times epsilon 4 equal to epsilon. So we are in less than epsilon. Okay, so we indeed true, right? This statement is true. So we know exactly what epsilon and delta are connected. We know what delta is supposed to be. So now we can choose any epsilon we want to be as arbitrary close as we want. And so, therefore, limit as x approaching 3 of 4x 5 is going to be equal to, right? So, okay, and now that was we used the full definition. But essentially, if we broke down the definition, right, if we break down this definition part by part, right, we will get the following two definitions. So we can get the definition of the left-hand side limit, the right-hand side limit, right? Let's take a look at it. So the definition of the left-hand side limit is essentially saying that, limit of f of x as x approaches a from the left is equal to L if for every number epsilon greater than 0, there's a number delta greater, such that, right, from the left side, and then this one's going to be approaching it, and then same thing from the right side, right? So now we're going from the right, so it's left and right side. So then if we combine it together, we will end up having the full definition of a limit. Okay, now let's go ahead and define the infinity limits. Right? We talked about them last time, but we haven't yet gave a precise definition. And we kind of have an intuitive definition of what it would mean. So the precise definition of an infinity limit would be, let f be a function defined on some open interval that contains the number a, except possibly at a itself. Then limit of f of x as x approaches a is equal to infinity means that for every positive number m, there is positive number delta, such that for x being an interval within delta, f of x is going to be less than number m. There's always going to be able to find that number m that will give us, will always be bigger and bigger and bigger than our function value. That means that the function approaches b. Right, similar thing we can do for the negative infinity, right? So For every negative number n, there is a positive number delta, such that for the interval within of x within the delta, the f of x will be always smaller than the number n we pick, right? So number n will be always, the function will always decrease. Meanwhile, in the previous one, the function will always increase. It always will be bigger than the actual, than the number we pick. All right, perfect. So now we will start for the next lecture. We will do the continuity and intermediate value theorem, which will already use the fact that we know the limits, the precise definition. So we're going to tell what does that mean for a function to be continuous, and we will know what is the intermediate value theorem of calculus. See you all next time.